Have you ever wondered what lies beyond the point of no return, where even light cannot escape? Black holes, the enigmatic monsters of the cosmos, have fascinated scientists and dreamers alike for decades. From their mysterious formation to their immense gravitational power, black holes challenge our understanding of space and time. Join us as we dive into the incredible world of black holes and uncover their secrets, exploring the science, the wonder, and the unknown. The formation of black holes, the birth of a cosmic giant. Black holes form from the remnants of massive stars that have reached the end of their lives. As a star burns through its nuclear fuel, it maintains a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. When the fuel is depleted, gravity wins the battle, causing the star to collapse under its own weight. For stars much larger than our Sun, this collapse leads to the formation of a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape. The gravitational pull here is so intense that not even light, the fastest thing in the universe, can escape its grasp. Not all black holes are created equal. Stellar mass black holes are born from the death of stars, while supermassive black holes, millions to billions of times the mass of our Sun, reside at the centers of galaxies. These colossal entities likely formed from the merger of smaller black holes and the accretion of vast amounts of matter over time. Intermediate mass black holes, a middle ground between stellar mass and supermassive, have been harder to find, but their discovery has opened new avenues for understanding black hole evolution. Their formation remains one of the great mysteries in astrophysics, providing a link between the small and the colossal. The creation of black holes is a process that illustrates the immense power and complexity of the universe. From the remnants of dying stars to the titanic forces shaping galaxies, black holes remind us that even destruction can lead to profound new beginnings in the cosmos. The anatomy of a black hole, beyond the event horizon. A black hole is more than just an abyss. It is a complex structure with distinct parts that play a crucial role in its behavior and influence. At its heart lies the singularity, the point of infinite density and zero volume where gravity is so intense that it warps space and time to extremes. Surrounding the singularity is the event horizon, often referred to as the point of no return. Once an object crosses this boundary, escape becomes impossible. The event horizon is not a physical surface, but rather a mathematical boundary defined by the black hole's immense gravitational pull. Outside the event horizon, many black holes are surrounded by an accretion disk, a swirling mass of gas, dust, and debris drawn in by the black hole's gravity. As this matter spirals inward, it heats up to millions of degrees, emitting intense radiation that can be detected by telescopes on Earth. In some cases, black holes produce powerful jets of high-energy particles that shoot out from their poles at nearly the speed of light. These jets are powered by the intense magnetic fields generated by the accretion disk and can extend for thousands of light years, influencing the formation of stars and galaxies. Understanding the anatomy of a black hole reveals the intricate processes at work in these celestial phenomena. They are not simply voids, but dynamic and influential objects that play a pivotal role in shaping the universe around them. How black holes warp space and time. Black holes are more than gravitational traps. They are cosmic engines that distort the fabric of space and time. According to Einstein's general theory of relativity, massive objects like black holes curve space-time, much like a heavy ball placed on a stretched rubber sheet. As a result, time near a black hole slows down relative to an observer far away. This phenomenon, known as time dilation, means that a clock near the event horizon ticks more slowly than one in a distant region of space. If you were to observe an astronaut falling into a black hole, their movements would appear to slow down as they approached the event horizon, eventually freezing in place. The intense warping of space-time also affects light. Black holes can bend light paths, creating a phenomenon called gravitational lensing. This effect allows astronomers to see objects hidden behind massive celestial bodies, as light from distant stars and galaxies is bent around the black hole. At the event horizon, space-time becomes so warped that all paths lead inward. Once something crosses this boundary, it is destined to fall into the singularity. This extreme distortion of space-time challenges our understanding of the universe and raises questions about the nature of reality itself. By studying how black holes warp space and time, scientists gain insights into the fundamental laws of physics and the relationship between gravity, matter, and energy. Black holes are laboratories for testing the limits of our theories and exploring the universe's deepest mysteries. Black holes and the cosmic web. Black holes are not isolated entities. They are deeply connected to the large-scale structure of the universe. They play a central role in the formation and evolution of galaxies, often acting as the anchors around which galaxies grow. Supermassive black holes, located at the centers of galaxies, influence the motion of stars and gas in their vicinity. Their immense gravitational pull binds galaxies together, while the energy released from accretion disks and jets can regulate star formation by heating and dispersing surrounding gas. Galactic collisions and mergers often lead to the merging of black holes, creating even larger supermassive black holes. These events release powerful gravitational waves, ripples in spacetime that can be detected by instruments like LIGO and Virgo. The relationship between black holes and the cosmic web extends beyond galaxies. The jets from supermassive black holes can shape the intergalactic medium, distributing energy and influencing the formation of galaxy clusters. Black holes are key players in the intricate interplay of forces that define the universe's structure. By understanding the connection between black holes and the cosmic web, astronomers piece together the story of how galaxies and the universe itself have evolved over billions of years. The Event Horizon Telescope. The Event Horizon Telescope, or EHT, represents a groundbreaking effort to capture images of black holes, allowing humanity to glimpse the unseeable. Using a global network of radio telescopes synchronized to act as a single Earth-sized instrument, the EHT captured the first-ever image of a black hole in 2019. This historic achievement revealed the shadow of the black hole at the center of galaxy M87, surrounded by a glowing ring of hot, spiraling matter. The image was more than just a visual spectacle. It confirmed the existence of event horizons and matched predictions made by Einstein's theory of general relativity. The glowing ring represents light bending around the black hole, while the dark shadow marks the region where light cannot escape. This discovery offered direct evidence of how black holes warp spacetime and manipulate matter. The EHT's success was a culmination of years of collaboration among hundreds of scientists and engineers. Data collected from observatories worldwide was combined using a technique called very long baseline interferometry, enabling the extraordinary resolution necessary to image a black hole's shadow. Building on this achievement, the EHT is now targeting other black holes, including the one at the center of our galaxy, Sagittarius A*. These efforts promise to reveal even more about the enigmatic nature of black holes and their environments, providing a window into phenomena that were once purely theoretical. The Event Horizon Telescope has opened a new frontier in astronomy, proving that humanity can tackle the most daunting challenges in exploring the cosmos. It is a testament to the power of global collaboration and the unyielding human desire to uncover the universe's deepest mysteries. The power of gravitational waves. Listening to cosmic collisions. Gravitational waves, ripples in the fabric of spacetime, are one of the most exciting tools for studying black holes. First predicted by Einstein's general theory of relativity, these waves are produced by cataclysmic events such as the collision of black holes. In 2015, the LIGO Observatory detected gravitational waves for the first time, marking a new era in astrophysics. When two black holes spiral toward each other and merge, they release an immense amount of energy in the form of gravitational waves. These ripples travel across the universe, carrying information about the masses, spins, and distances of the merging black holes. Observatories like LIGO and Virgo capture these signals, allowing scientists to study cosmic events that would otherwise be invisible. Gravitational wave astronomy has led to several remarkable discoveries. It has revealed the existence of binary black holes, confirmed theories about their formation, and provided insights into the nature of spacetime itself. Each detection expands our understanding of the violent and dynamic processes that shape the universe. The study of gravitational waves has also opened the door to exploring the unknown. By observing waves from black hole collisions, scientists test the limits of general relativity and search for evidence of phenomena like primordial black holes, which may have formed shortly after the Big Bang. Gravitational waves are more than a breakthrough. They are a new way of experiencing the universe. They allow us to listen to the cosmos, unlocking secrets that were once hidden in silence and enriching our understanding of black holes and their dramatic lives. Black holes and the nature of information. Black holes present one of the most perplexing paradoxes in modern physics, the information paradox. According to quantum mechanics, information about the physical state of matter should never be destroyed. However, when matter falls into a black hole, it appears to vanish beyond the event horizon, seemingly erasing all traces of its properties. This paradox challenges the foundations of physics. Stephen Hawking's groundbreaking work on black hole radiation, known as Hawking radiation, suggests that black holes emit energy and can eventually evaporate over immense timescales. Yet this radiation seems to carry no information about the matter that formed the black hole, intensifying the puzzle. Physicists have proposed various solutions to the paradox. One theory suggests that information is encoded on the event horizon itself, much like a hologram. This concept, known as the holographic principle, implies that the universe's three-dimensional nature may be a projection of information stored on a two-dimensional surface. Another idea is that information may escape through subtle quantum effects during the emission of Hawking radiation. These theories are still being tested and debated, but they represent profound implications for our understanding of quantum mechanics, gravity, and the nature of reality. The information paradox demonstrates that black holes are not just astronomical objects, but philosophical and scientific challenges. They force us to reconsider fundamental assumptions about the universe, bridging the worlds of quantum mechanics and general relativity in a quest for a unified theory of physics. The ultimate fate of black holes. Black holes are not eternal. Over incredibly long timescales, they lose energy through a process known as Hawking radiation. This phenomenon occurs because of quantum effects near the event horizon, where particle-antiparticle pairs form and one falls into the black hole while the other escapes, carrying away energy. As black holes emit radiation, they slowly lose mass, shrinking over billions or even trillions of years. Eventually, a black hole will evaporate entirely, releasing a final burst of energy before disappearing. This process, though theoretical, has profound implications for the fate of black holes in the universe. In a far distant future known as the heat death of the universe, when stars have burned out and galaxies have dispersed, black holes may be the last remaining objects. Their slow evaporation will mark the final stages of cosmic evolution, leaving a cold, empty expanse. The study of black hole evaporation also sheds light on the interplay between quantum mechanics and gravity. Understanding Hawking radiation could lead to new breakthroughs in unifying these two fundamental forces, offering a glimpse into the underlying fabric of the universe. Black holes, born from the fiery deaths of stars, ultimately fade into obscurity. Their life cycle, from colossal gravitational monsters to evaporating whispers, symbolizes the incredible transformations that define the universe's story. They remind us that even the most powerful phenomena are not immune to the passage of time. The mysteries of black holes inspire awe and curiosity, challenging us to expand our understanding of the universe. From their formation to their profound influence on space and time, black holes are among the most fascinating phenomena in existence. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep uncovering the universe's secrets with us.